Hello there. So we're starting with calculus now. We're up there now. So the first thing I did was go to definitions and limits. It's kind of clear by the arrow that is approaching something that is what a limit is. And once you plug something and you get something, the limit is done. Actually, I think I already talked about this section. So I'm going to move on to a section that I didn't talk about. I think I did talk about the definitions here. So we're going to start with the discontinuity, which there's a few types. A jump discontinuity, which is kind of obvious when you go here and it suddenly goes somewhere else. Technically, right now, we consider this limit that's not possible. But in reality, in what's it again? Forward series, you're gonna allow this middle part to be. Um, right now, you don't know that it's shenanigans, so you don't have to know about that. But that's for the future. Me to explain later on. And over here, you get a piecewise smooth up to here, and then we see another jump discontinuity. And over here, you see over here, we have a remove discontinuity. This remove discontinuity does not invalidate this limit. The limit is over here because it's approaching. You're approaching from the left, approaching from the right. That is what a limit is. We'll do a more formal definition later on. Did we talk? No, we didn't. Okay. So next is the infinite discontinuity, or otherwise known as the isentrope. That basically at infinity over here, negative infinity, there isn't anything. So you can't really say anything over here. So that's the next one. And then oscillating discontinuity, which is overcoming or pushing and going like this to the point that you can't even tell what is the point, basically. You can't really tell where it's approaching, and therefore the limit does not exist. Oh yeah, I did talk about limits finally. So a limit is a direction. Yeah, Hody. Yeah. So here's a is where I show off limits. Basically, this is approaching to the right, and it's approaching to the left in the same direction. So the limit exists as a normal limit. Obviously, one side limit exists over here too. At point B, obviously it's approaching something, so that point is this, even though there's a discontinuity where this is where the actual point is. Over here, clearly this is a DNE because it's approaching two different places without anything. So in 3D, you can imagine the limit does not exist for anything unless every single line goes into one point basically, which is 3D. And 3D is more painful, but not right now. We're gonna do 1D first. Oop, go to making that mistake 100 times. Um, Here clearly we see cosine. So this limit is d at infinity. So as you go to negative infinity or infinity, basically keeps on oscillating. So there's a dne over here. And infinity is a big topic because infinity actually exists. And here it's the first thing about limit is that if you plug in a continuous, if you plug in a number in continuous equation and get an answer, then that is the limit. So like 9 out of 10 times, if you can plug in and get an answer, that's the limit. I haven't seen a case that doesn't have it, so I guess 10 out of 10 times for now, because I haven't seen a case that doesn't do that. We're going to do some Taylor series version of it, so maybe there we have some kind of minor. Why is this not 14? Okay, that's weird. If happens, did that break anything? No. So I don't know why that wasn't 14. Sorry about that. Over here is a bunch of one-sided limits. And is there no. So if you go this way, the limit does exist for one side, which is no, sorry. This doesn't exist because there's another one over here that was covered up accidentally. This way over here, there B. I'm pretty sure there's no other ones. So this one, the right hand side is this. This one doesn't. This one exists. It's the left hand side. So yeah, that one exists, right? Because there's one thing over here. Over here, there's two direction, and they both go to nearly zero. So basically, that exists. All right, that's good. All right, let's go. Over here, I think this was infinity infinity, but because it's negative infinity and infinity is DNE for the most part, as you can see, you can check by using left hand and right hand limits. Um, and then basically over here you see that it goes to infinity, therefore it is infinity, but it's kind of hard to see. I didn't expect it to be this hard to see. Um, oh, didn't expect this at all. I was not expecting this. Honestly, was not. Um, does that make it cleaner? Yes, it does. And then over here, let's just make this bigger. Uh, is this okay? I think that's much better. Let's hope so. It's visible now. So next, oh my God, did we not cover any of this last time? I don't think so. Oh my God, there's so much to cover. Um, over here we have a conjugate. Basically, you multiply square root of x plus one minus version, so you can collapse the all the square root. As you know, square gets rid of everything, and you do the bottom and the. Did I make a mistake here? I think I did. This is supposed to be a minus here. This is not supposed to be a negative, and this is supposed to be a minus here, and this is supposed to be a minus here, and then this is a minus, then this is a minus. Therefore, the whole thing is a minus. I did not make a mistake there. Oh well. Over here, I kind of cheesed it a little bit here by bringing in Taylor series, but it's really not Taylor series because it's kind of obvious with the sign. But that's why I gave you a given over here, but this is how you solve it. And over here is like knowledge of functions, basically. We know there's an isotope at arctan, which is it arctan or tan? No, arctan is like this if I remember correctly, and it's pi over 2 over here, and it's just knowledge. It's just a little bit of knowledge you need to know from trig. So here's an area of circle. This is actually taking a longer time than I thought. There's a lot of things I changed in such a short time. That's why I need to make a video every day. Otherwise, there's too much to talk about one day. Area of a circle. So here, as you can see, we have the classic go to geometry, and you can figure this out. You realize that this can be R and R for a circle. And then after that, you realize the whole entire 360 is 2 pi, and then you divide by n to make it infinitely as small, because n is going to be the thing that we take the limit of over here. So that means that we have the equation of a triangle. We have the angle over here that we can just plug C in. And then we have RR. Oh, and we have N just because we're going to say that's the amount of times we divide it. So we have everything and to take a limit of that. So here is the form a genuine circle, basically. This is a genuine circle. Um, Over here, as you can tell, oh, is it working? Yes, it is working. All right. So here, if you take a limit of this, and then you realize that sine theta needs to have this, and here I showcase it a little bit, and I'm pretty sure if I control plus over here, you can kind of see it, but I'm pretty sure if this is printed, it will be cleaner. But over here, you can kind of see that at point zero, sine and x like something like that is the same. Why is that important? If you look at this, I showcases that it's only when theta equals 0 that this is true. Now that needs to be clearly laid out when we do this. So that's the only case where, yeah. Anyway, that limit gives you that. So yeah, clearly I show you all the steps properly, so it's not hard for you to figure it out in the end of the day. So I hope you just look at it and you realize, yeah, just follow the steps. Over here, these two are needed for the derivation of cosine and sine. So you can't use la hop. Cannot use la hop yet. So yeah, this is kind of it's a lot of trig identities, but once you realize that, it's kind of simple. So this is like you already know this one. This one is a little bit more tricky because you have this over here, and you're gonna have to use this how to get to here, which is a trig identity, but it's not an obvious one because you're gonna have to because I believe the it's like sine 2x, so you have to equals 1 minus cosine 2x divided by 2 or something, but because you have to reverse engineer it, it's x divided by 2 and multiplied by 2 of the sine square, so that's how I got it. It's not obvious, but you can get it. And why is there a t here? Genuinely, why is there a t here? What the hell? Yeah, I don't know why there's a T there. Let me delete that. Now the next question is why is it x divided by 2 over here? Well, if you really think about it, sine x divided by square is 2 sine x divided by square. And we already discussed about this rule. So we could just say this is x divided by 2 multiplied by x divided by 2. And we have a 2 over here that cancels out with 2. And we have x over here that cancels out with this x. So we have left with x divided by 2. So over here we have x divided by 2. That's basically all I did. Excuse me. Uh, so we go on. Oh, wait. Why? What the hell? Okay, I was wrong. So you could have done that. I chose not to for some reason and instead have to use sub over here. Um, not use sub, but substitute t equal x divided by 2, which would give me this version, which yeah, I guess that works. That was the lamer version. But yeah, I did not expect me to use the lame version, but I did use the lame version. Either way, I get the right answer. Who cares? Um, Anyways, over here you find the limit of s. Yeah, so you just have to use the left hand, right hand, and get this. It's not hard question. Just need to put that. Squeeze theorem are my favorite thing to use for fucking integral proofs because they're everywhere there. Basically what this saying is basically if you're gonna get a limit of this, why not take because it's gonna oscillate at infinity, why not take the negative and the one version of it? And if these two go to zero, but by elimination, this has to go to zero, and that's basically what happened here. We take the left hand, right hand, and then we just find that it is basically zero. And I can do this again, but it's just doing the same thing. And this is just more complicated versions of it. Oh yeah, this is just more of those. I don't worry, there's a harder questions. I'm just skipping some of these because, well, there's no point in doing some of these questions. Well, I mean, there's point to do it for yourself, the like practice question, but there's no point for me to just go through them because you kind of know how to do it after a point. But I can explain to you if you want, but yeah, I don't want to. If I feel like I want to, I will. But most of these questions, like some of them are just like I don't think you need to. Yeah. Anyway, the formal definition of limit is this over here. This is the formal definition. This is like the boss level, and there's a few limits that actually I should explain everything. Okay, I'm gonna go back there. Okay, so basically here I should still explain this shenanigans at least a little bit. Over here, you see over here, and you see how I got this version down over here. That's because you see over here x just is one, and then that's just a cosine x is left over. So over here I realized you could get the left hand, right hand, and this is equal to zero, this is equal to zero. So this must be equal to zero. That's basically all I said. And then yeah, I did the hard way again because once this is zero, you realize that this is one. So I did the hard way, but you can. I I'm starting to realize I used to, because some of these questions I made a long time ago. Some of these questions I made is doing the hard way. I don't know why I chose to do the hard way and the difficult way. Um, Anyways, B over here. I mean, you already did this actually question. The only reason I want to show this off was because I want to show B and A like a more of a formal way where you can go any case like this, you can get a big negative answer, and that's just infinity, negative infinity. Oh, this is just negative infinity, but you get what I mean. Oh yeah, negative infinity over here and negative infinity over here. What's the answer to this? This is 2A. And over here, I don't know why I made this question like this, but it's a good exercise, I guess. Here, this is a little bit tricky question because this over here goes to zero. This and this is what's the right word? It's not just zero because of how it's set up. Because it's a logarithmic. If you know any of the log properties, you can't just say something is zero. And basically what I did was I made them into one consider unit because if you do this, this is just an operator at this point, so you can drag that out. An operator doesn't affect the internal. So over here you have this to this. So you just have to calculate that, but then you realize that this is -1. And -1 causes error unless you go to imaginary coordinates. So you realize this is the answer afterwards. So imaginary number to the rescue, and imaginary number works like any other, like it just works like any other like number basically. Over here we have the formal definition of a freaking unit, a limit. Over here, if epsilon is greater, then there is this delta less than, and so on, so on, so on. Well, I hate this definition because it's a pain in the ass to use, and no one uses it in real life, except for some proof that you need to do in the basic level. Because some proofs. So here's the thing: the only reason I brought this up is just for one exact reason. This proof over here. So you need this to prove ln log or no, natural log derivative. You need it for exponential derivative. So all of this is for this one tiny proof because I didn't want to do a reciprocal. Basically, I didn't want to make it so that basically you need this to prove this, but you need this to prove that. Basically, you have a looping definition. Like continue, that's not correct then. That's not a proof then. So I needed to prove this. So then I thought I couldn't figure any other way because you need to use the Hop or Taylor series that all require some pre-knowledge of a derivative. So what did I do? I went to the most fundamental type of proof, which is epsilon and delta proof. And this is goddamn painful. Yeah. And it has a lot of ideas of squeeze theorem. So if it sounds a lot like the squeeze theorem, because it kind of is, it kind of is. It's basically saying, oh well, if you do this over here, yeah, that works. Yeah, this epsilon delta 2 over works, and then over here you realize it's greater than that, but you realize that this means this, which means basically is going for if because of this over here. So this is over here, so -1 because of that. But you're basically dragging it down like squeeze theorem, going down to zero, and basically saying, well, this is the only answer. It's going this way, it's approaching this way, it's approaching this way, and you're squeezing it down to there. It is basically squeeze theorem. It is one way or another squeeze, but it's a painful one because it's pain. Because no, I don't think anyone likes to do this one. Yeah. Anyways, you can kind of tell that it's not true when it's like when this happens. Basically, oh well, it violates is equal to, not less than. So that means it's wrong. It happens a few times. So And that's well, anyways, there's another case over here where I show that epsilon equals delta. Yeah, that's fine because it's less than, it's fine. Over here, we do another painful question, but you finally get delta equals less than, and then you realize this is where's the C at? C at is a 7, and I forgot why this works. I made this long time ago, but basically, it turns out it just goes into basically satisfies, I believe, this condition over here or something. Yeah, this condition, therefore it's just squeezing down to this place over here and it's going down to zero. Basically squeezing to that place. Again, over here we have the same thing, and over here we squeeze down over here again, and yeah, this is the proof thing. And you can also show. I just want to show a case that it does go to 2.17, but yeah, it basically squeezed down to that place. So it's actually, and technically, I did kind of not explain a little bit over here. This is actually the binomial, little bit of binomial, but. It's not really that difficult to do it by hand, so I did not just go to binomial. Oh, why is this here? Oh, I thought I deleted the all. And obviously, I can prove all of this with the epsilon delta, but at that point, I was tired, and I was just saying, just look at the graph. I'm done. Because yeah, technically you can prove that. I'm just gonna say, look at the graph now. Just inspect by graph, and that's why I said afterwards, like, nah, I'm not doing that for shenanigans. And I just say later, there's no. That later is the epsilon delta proof. I'm not doing that shit. So I'm not. And then that's what happened. So basically, here's your I'm tired moment. Anyway, so we then go into proving limit definition, derivative chain rule, and more derivatives. And this is when I lose my mind because you'll see over here that we go over here, which is the first thing. A derivative of a number is basically zero. No matter what you say, any constant is nothing when you take a derivative of it. And if you have a constant in a derivative, it becomes you can pull it out. Now, these two properties don't really explain what the hell the derivative actually showcases later on. So we actually do it for formal questions of this. So we did what if we put that a function is x squared. Now, we have to showcase a limit of that. So we finally get to here and we see a h is goes to 0. So if you do that, you'd find out it's 2x, which, great, we have solved it. Good job, everyone. We've done it. Um, yeah, so this is a power stereo, it's powerful, but we're going to prove the power rule later. Now, here's the la hop that we need to know. So we start from here. We realize that we can do a minus GD over here. Why can we do it? Let me look here. Why can I do it? I don't remember actually. Oh, so this is plus one. And from that, you get this formula, which if you take a limit here, you get this. I think there's a mistake here. Maybe there is. Because I'm pretty sure it's minus F. Huh? I'm gonna double check my little hop proof later on. Something doesn't feel right. Oh well, I know the hop works. Let's just clarify here. The hop works one way or another. Um, yeah, I'm gonna have to double check that proof. That proof seems dangerously wrong. That's a good catch. Here's more the power rule for actuality. But I know a lot of you just say just move on because it looks painful as hell. I could have actually used binomial theorem, I realized, to make this life easier. Uh, you know something? Yeah, I could have totally used binomial theorem. Why did I not use binomial theorem? Well, well, it looks like my earlier life wanted to make my life harder and do this method. So this is what you start off with, these two. So you start with this one, I guess, and you multiply by x here. It's been a long time since I did it. So and then you do a little bit of algebra to get this format over here. And you x is this over here, so you have to plug that back in over here to get this format over here. And now from that, you get basically x minus an, x minus an. You do a little bit more algebra here, and you finally get this format, which you could take a limit of x to a. Why can you take a limit x to a? Well, it's because to think about what is what we started off with, which is this form. It's another way to take derivative. So we're just taking a derivative of it. We're taking a limit base of it, and I need water before I lost my mind. So basically what's happening is that we're taking a limit of it and to see it's just a derivative basically. Let me get my water. Anyways, that doesn't explain why you have to take x to a again. Uh well, you have to think about it. What the hell did I say? Well, I said an minus an. Huh. So an minus an. Um and then why does a matter? What the hell does that mean? Right? Um and then you have to realize uh try to get xn, right? So I actually genuinely forgot, so I'm thinking in my brain why this works over here, and I genuinely forgot. Oh no, I'm stupid. This is just taking a limit of it, so x equals a basically because of the derivative. Yeah, over here. So over here, you just do that and get in and and then that's obvious. What am I doing? My 3 o'clock binger is taking forever. Right now it's 3 o'clock a.m. When I was supposed to sleep like 3 hours ago. So over here we do a bunch of la hop. It's just la hop. Derivative on top, derivative on the bottom. I'm definitely sure this is wrong. This over here tells me something's wrong. I'm gonna have to fix that. All right, and then yeah, yeah. This what did I do here? Either I'm wrong or I'm a fool. Either way, I need to fix it. Um, yeah. What could I possibly have done wrong here? Yeah, I don't know. Well, technically speaking, I don't know. I'll figure out later, but I'm pretty sure I did something wrong. Unless, yeah, I'll figure it out. I'll figure it out, and I'll come back to that again. But anyways, I'll probably have to look to textbooks tomorrow because I'm very sleepy right now. I don't want to look through all those textbooks. Um, over here is I need to really sleep. That was basically what I'm saying. I'm sleep deprived right now. Over here is plus h over here, and then this x, and then h. We get ex. That's what we want. So what do I have to do? So we simplify first, and we move the ex because the h is the only one that's actually active. Over here, then we do a little bit of algebra and a bunch of other things to get this. So we can actually get this as our starting base, basically, because of all the algebra we did. And then we realize that basically equals 0 because this is 1. And that allows us this step, basically, and you finally get this format, which we know equals 1 from our experience, from previous sections, the epsilon delta proof. This is the first time we'll use epsilon delta. And we'll use it again over here for ln of x. Over here, as you can see, another epsilon delta. So we get this in the end. Um, you can check out that proof. I did it multiple times in other videos, more detail. So over here, we have the cosine sine proof again, which we have over here, our famous limit that we needed, and another famous limit we needed over here that we showed off in the previous video, in the limit section. Again over here, oh, and then the same thing with sine and cosine. And then we do a chain rule, which is important because we do a particle afterwards, which I explained in a previous video extensively on these two, and the quotient rule too. Um, and basically after that, we do a bunch of questions after we derive all this. Bunch of questions that you can check out. They're all pretty decent. They all does something about it. And I cleaned it up a little bit so that it has some like uses, some here and there. It's not that hard, but you can actually feel the uses. And then we do the Pascal special dimension number. The easiest way to do one of these, basically, if you have a bunch of particles that to do, um, and then we do absolute min, which I need to make more questions of, so I'm going to skip it right now because I didn't change anything there. And then we do intro to Riemann sum, basically. So over here, I can see these two over here needs a little bit of touch up, and then I need to touch up on Laha proof because obviously I fucked up there. If I didn't fuck up, that means that I forgot something, but and then, it's been such a long time since I did that proof, so we'll see. So reverse over here, we know that the integrals are reversed. We did a bunch. I just showed up a bunch of them over here, but that doesn't do justice. So we're gonna do the fashion way where we do actually maybe this should be another video. Yeah, I'm gonna stop here and I'm gonna stop recording